Okay, so this is the name of it. It's about how to if we are transport a single pallet or if we do it in a batch with a train. That is the background of this. So what we have been working for at with Scania for quite many years now is a train supply. So something around 2010 or something like that, we introduced train to supply material from our picking platforms or supermarket to the line. So we have been developed that now during the years. So we have a concept that's called mother and daughter. So we have like fixed wagon, the red one, and then we have the cart, and they are called the daughters. So we can easily insert the daughters, go out to the line, and then take them out and supply them to the line. We introduce tag, so we know if the line is going in the tag. We have also logistic tag, so if the line stop, our train will stop. And we also have a specific way how to configure the different cards. So it's working quite well. But it's still 100% manual. So there is a driver driving maybe up to five trains or wagons behind. And every time we supply, the driver needs to stop the train, goes maybe 20 meters to the last wagon, and then manually take out the cart, drag it and push it into the line and take the empty one and bring back in the train and then go back. That's the way you do it. And just to understand that we have different workshops and they are designed as they are, and that affects the way the solutions that we are looking into. So this is one example of a logistic in the yellow one. This is from Zolle in Holland, and this is the production, the green one. So we go from the yellow to the green and bring the material, and it could be up to 900 meters, and all trains or material must pass this one. So you can imagine this is really a bottleneck. So what they have done there, they understand it. We need to have train because we can't allow to go one by one. If we look at another workshop in Södertälje, we have supermarkets more distributed. We have up to three areas and plenty of openings so you can easily go in and out. In this workshop, we are most likely go for a single piece flow. So we take them one by one because the distance is much closer. So the distance to travel maybe a route is about 200 meters. And then, of course, we have this big thing now that we are looking into. We would like to automate. We would like to, and maybe the trend about AMRs, AGVs now is booming everywhere. You can find a lot of automation in this area. And we want to have 100% automation. We want to deliver the parts to the line without any humans at all. And that is, of course, then the challenge, especially with the train. So if we look at the single piece flow, these are some concepts that are available on the market that we are looking into. We can start with this one. We have fixed racks at the line side or wherever we pick up and drop. So they are bolted in the floor, and the AGV here in this case goes under, lift the pallet, and carried it on during the transport, and then go to the next fixture, go inside and lower it down. That's one concept. Another concept is that maybe you have seen Amazon when they run around in their storages. So they take an underride, go inside the cart, and then lift the cart, and on top of the cart there is also the pallet. Move the whole cart to the line and drop it there and go away. That's another concept. And then there's also concept of like fork over leg AGVs. So you are able to just take the pallet and then you can go to the line side, and then you can have, of course, different heights, and you can use the forks in order to place the pallet at the best place or the best height. So these are three concepts that we are looking into. We don't know yet which one is best. We are installing that one right now and that one, and we are looking into a solution of that one. So it's still a big area to understand what's the best. And then, of course, how to do this with the train, and that's maybe the key thing here, because what we do right now with train, we have automated transport. but there are still people today that will do the transfer from the train into the line. The next step is, of course, how to do the last automation if we want to automate, and that we want 100%. There are some concepts on the market, but we're not there yet. But this is the next challenge. So either you can use this under right type, in this case, you go under and lift up the daughter, and then you can bring it to the line, and then take the empty one and load the tray. This is another concept that you have more roller conveyors at the line, but then you need to align the train to that conveyor, and that is not easy. It's maybe easy if you have a straight line, but if you have a line that goes a little bit like this, that concept will be very tricky. But that's something to continue to study. So that was the background, I would say. So now I hand over to for you, please.
You. Like that. Yeah, so as Lennart said, there are many challenges with these batch deliveries, and in this study that we have performed, we're looking into one of those challenges, basically the dimensioning, or how many AGVs you would need if you have, when you vary the load capacity, how many wagons you should include in that kind of batch delivery setup. So in this study, it's been me, together with Robin Hansson, Patrik Fager, and Marcus Franzén. So just to give you an idea, it's these types tugger AGVs that we're talking about. They don't have a driver, and they make these deliveries in the assembly area. So from previous research, it's mostly on AGVs, then it's mostly focusing on these single load AGVs, some kind of forklift AGVs or some underride, and it's not that much focus on the multi-load or AGVs having a load capacity larger than one unit load. But there are then some potential effects of using a larger load capacity. You could have a shorter distance per delivered unit load, cause less traffic in the environment, less risk for congestions. But then there is also a chance that you get longer delivery times. Completing a delivery cycle takes longer time, so might cause waiting transport orders. And it can also be more difficult to control. You have to be able to utilize the load capacity in a good way to actually make use of this batch transports. And then it's of course important to decide on this load capacity, as it influences how many AGVs you need, and that's a big part of the investment decisions. And what we're looking into in this study then is different conditions in the material flow. How does that influence what kind of load capacity we should have, and then the required fleet size to meet the deliveries in the material flow. So the purpose, how conditions in the material influence the minimum required fleet size of AGV systems of different load capacities then. And we're looking into a mixed model assembly. As I said, single load AGVs has been in focus mostly, but there are some papers looking into this, or some research basically looking into multiple load AGVs, looking at the dispatching and scheduling to when to start the delivery. And often this is in job shop environments and not so much in these mixed model assemblies. Some conditions have also been part of this research, of course, but they have been used to test different these dispatching algorithms. When are they suitable, but not so much into this question that we are looking into in this paper. And as I said, quite limited attention in these mixed model assembly environments. So we have developed a simulation model, a discrete event simulation model, which has a starting point in industrial material flow. So it's based partly on a actual material flow. And in the current flow, this material flow is performed manually by a tugger train, but we're then looking into how it could be performed by AGVs of different load capacities then. So we have tried to replicate the demand in this material flow and how the demand is distributed over time. So how many transport requests are generated and then how they're approximately distributed over time. We have also recreated the general layout, the distances, and the localization of these transfer positions and the starting positions, as well as then the traffic rules. Basically, there's no overtaking in certain parts. Certain aisles are unidirectional. You can only go in one way. So to replicate this material flow in a good way. We have also developed then a dispatching rule to start the delivery. When do we have to leave the storage area and go to and perform a delivery? And it's currently based on the experience of this manual tugger driver. They decide on when to go, but in the model we have used we based this decision on there is this requirement that delivery should be made within 2,400 seconds from when it's created, when you have picked the last item and scanned the barcode. Then the delivery should be made within 2,400 seconds. And we use that together with the traveling distance to calculate the maximum waiting time for each transport request. So we know now we need to go to be able to deliver on time. So this is the general layout, and it's similar to what Lena talked about. It's long distances. It's approximately 750 meters to drive around here, which makes this kind of batch deliveries interesting. So this then represents the material flow that we've studied. But we also test then single load AGVs, and for that these AGVs can take different routes since they're more flexible. They can turn around anywhere in the layout. So for that, for the single load AGVs, they can actually move in both directions here in this material flow. And as Lennart said, it's a starting point from one storage position where it's a lot of traffic. So again, batch deliveries could be suitable. I talked about material flow conditions before, and we have 4 conditions that we investigate: the production rate, the demand, how many transport requests are generated, the AGV speed, 2 levels here. We have also a variable for introducing some disturbances, and that should represent that if there are other traffic modes, forklifts, pedestrians, other tugger trains moving in the layout, which interrupt and cause delays in the transports. And finally, we have this time windows, which I talked about, the time from when a order is generated, transport order is generated until it should be delivered. And as I said, we're looking into what is the required fleet size to meet the demand of this material flow. Some results then. We can look into these first here. We can see that going from a low production rate to a high production rate, or going from a low traffic interference to a high level of traffic interference, we see that the graphs for the load capacity 3 and 4 basically become the same. You need basically the same number of AGVs for both these, for both load capacity 3 and 4, indicating that perhaps load capacity 4 is too large of a load capacity utilized in a good way under these material flow conditions. And here we look at the average minimum fleet size, looking at to see the effect of each of the conditions individually. You can also see that basically the reverse is true here when going from a low AGV speed to a high AGV speed, or from a strict time window to a more lenient one, where the difference between load capacity 3 and 4 in the minimum required fleet size becomes greater again. We can also see that the speed it's the greatest slope basically for each of these load capacities here. And for the single load, it drives by far the longest distances, so it's of course a positive impact here. And the same is similar for low capacity 2, which also drives long distances in the environment. Looking then into the traffic influence here, we can see that the slope of the curve here is the greatest for the load capacity 1, and that this means that they have the largest fleet, and that means that they interact and they cause congestion with each other, causing delays, meaning that a larger fleet size is required under higher traffic interference. I said before that it's important to be able to utilize the available load capacity in a good way to actually benefit from the larger load capacity. And in this case, we can see here that for low AGV speed or strict time windows, we see that for load capacity 4, the utilization of the available capacity is not that great. And as we saw in this graph before here, we can see that the difference between load capacity 3 and 4 is quite small then. Just a brief mentioning, there are also a lot of variations in this model in how transport emissions are generated over time, which then affects the fleet size or the minimum required fleet size. Sometimes it's quite few emissions generated, while other times there are a lot more, and the fleet size should then, of course, be able to manage the peaks in demand as well. So the deliveries are not made late compared to this time window I talked about before. So I talked about that, and as Lennart talked about, there are many practical challenges how to make the actual move from the AGV tugger train to the delivery location and then back if there is a return flow or pallet back to the storage area. And in some cases, it might also involve moving leftover material from one bin to a new bin coming in, which is also a difficult issue. But that is a potential for a future study. And there are, as Lennart said, some solutions being developed on the market. So something that we could look into in a future study here. We could also look into, for this model that we have, additional dispatching rules could be tested, as well as looking more into these variations, which we saw had quite a large effect on the minimum required fleet size. But with that said, open up for questions.
You mentioned that you have some zones which are high congestion areas. You also mentioned that might vary over time on shift, right? So have you had any? You mentioned that you had rather intelligent AGVs that could pick other directions or
it depends on.
Can you open up new transport aisles or possible routes during certain times?
Not in the model. You depending on which missions that they collect.
Yeah, they have a predefined route, and that's the one they have to pick.
Yeah, but then if we go back to the layout picture.
That could be a human could possibly pick another one.
Yeah, but there are some delivery locations here, for instance. But when departing from the storage, if they don't have any deliveries there, they can just drive past this one, and continue.
All right, yeah. So if it's in the planning, basically, that they don't have a pickup.
Yeah,
it's not due to congestion. So
no, but that's
There are systems working, like you need like a taxi system, but for AGVs that can see where all AGVs are, and then that system can assign a specific route to a specific AGV. That is possible. But also remember, in the starting point we will not start with 100% automation, so we will have a very mixed environment. So in the beginning, you have very few AGVs. So then I also think it's important that we also keep track of the manual forklift or manual.
Right, because they might be doing a little jobs where.
Exactly. So and also maybe we should think of also giving the manual forklifts the routing, because today they decide where to go by themselves, but they don't know, for instance, if there's an AGV train standing in a specific area. So if they had that information, you can help the human to go another way, exactly like Google Earth is working. the map functionality in the car. That could be. There are companies working in that direction for this. But then you need a localization services for the forklift. And of course, there are different technology to handle as well.
I was thinking because if we look several years back, we've seen a lot of non-value adding AGV transportation. They move around a lot. So is this train transportation, can it solve some of the losses that has been in? Is it can you see any efficiency gains in using trains? And where you maybe want to use a single AGV because it's automatic, but it would be better to have an electric train instead.
I think in general, the longer distances you have. There are other transport. Now we are from the supermarket into the line, but we have interfactory flows, for instance, where we are transporting pallets from one factory to another factory. There for sure we can use AGVs as well. But I think still the train solution as we have today, we haven't solved the last millimeter delivery, and that's the big challenge, because every time you have another handover area, that will cost you extra handling, it will cost you need delays, and you need the planning for that area as well, and I think that is tricky actually. And again, to run directly from the supermarket and go directly to the line, that is really tricky. That's my feeling at least. Yeah.
I'm lucky enough to work with AGV simulations as well. And one of the constraints that we have in our factory is actually the charging, the AGVs, the batteries. It's a lot of non-value adding time when the AGV has to take off from its normal route and go to the charging station, bring the battery and go back. Have you thought about this here, or like how is this?
You mean in the simulation?
Yeah, or like in the calculations in general, or because one of our concerns were actually like AGVs that were heavier. So let's imagine that the AGV is carrying more parts. These parts were heavy. The battery was actually going down very fast.
Drained a lot,
Yeah, okay. And those things we had to consider in some simulations, and it was difficult calculation here, a difficult balance. But I don't know if you have the chance to do that math, or
not yet, or not in this one.
It's really like specific for certain.
Yeah, but charging is it's a huge area. There are different ways of doing it. You could have contacts, you can have wireless charging, you can do in loop charging, or you should have separate rooms to do the charging. So it's definitely an area to look into. It's important. Another thing that you can think of course, you can use the AGVs to charge during breaks. So that there are other opportunities that you could charge. But I know, for instance, in Zwolle, that's actually a good thing with the TOW train. They have chosen a battery that can last over a shift, only 2 shifts. So that is not a problem with the TOW train solution. But when it comes to smaller AGV, yes, we need to charge them during production or the opening time. So
very good presentation. Very good. Very good.
Anyone else? Okay. Thank you.